All right, today's physics video, we're going to be talking about the Doppler effect. So here we go.
Before we get into what the Doppler effect is, I need to share this with you. One of the things that's a little bit tricky about this is that there are three different velocities you got to keep track of. All right, the wave itself is carrying energy, right? If you're talking about a sound wave, the velocity of the wave would be, 340, 346 meters a second, or whatever, depending on the temperature of the air. If you're talking about a water wave, the velocity of the wave would be the velocity at which the wave sort of rolls, away from the boat and towards the shore, or, whatever, the boat creating the waves. All right. Now, because there's a wave, there's also a source of the waves. Something is creating those waves. And if that object is moving, then there's also a velocity of the source. All right. So examples might be, if you've got a boat moving through the water, it creates waves. The boat is the source of the waves. So the velocity of the source would be the velocity of the boat. All right. When a jet flies through the air, it makes sound waves. And because the jet is moving, it's got a velocity. All right. A sun, for example, creates light waves. And the sun, moves through the galaxy. And because the sun is moving, it has a velocity. All right. Now, there's also an observer. This is the person or thing that is hearing or seeing or experiencing the waves. All right. So let's go back to the boat. Imagine the boat, sort of slowly moving through the water, creating waves. And you're in an inner tube floating nearby. Well, you're going to get hit by those waves, right? Now, it's possible that while you're in the inner tube, you could be moving, right? You could be paddling, you could be being pulled by another boat, or whatever. And so there, you're the observer, you're the person being hit by the boat's waves, and you could be moving, so you could have a velocity. All right. As the jet flies overhead, you might be on the ground listening to it. If you're moving, you're the observer. Well, even if you're not moving, you're the observer. But if you're moving, you would have a velocity, right? And then similarly, if you're on a planet looking at that sun, the planet's moving, so you're going to have a velocity because of that. All right. So there's two objects, the source and the observer. The source creates the waves, the observer experiences them, and then the wave itself also has a velocity. All right. So moving on. Here's the definition of the Doppler effect. The Doppler effect occurs if either the source of the wave or the observer of the wave are moving. And what happens is, if this happens, the observer is going to experience a different frequency than what the source is producing. Okay? Yeah, let me leave it there, at that for now. All right? So, as a result of that, there's two different frequencies. All right? There's the frequency of the wave that the source creates. All right, so the boat moving through the water is going to be bouncing up and down, creating waves with some frequency. All right, there's also the frequency at which the person floating in the water gets hit by. All right, so this is the frequency at which the boat is creating waves. The frequency the observer experiences would be the frequency at which he gets hit by the waves. Okay. Talking about the jet, there's the frequency of the sound produced by the jet. And then there's the frequency that the person on the ground hears. Talking about the light waves, there's the frequency of the light waves emitted by the sun, and then there's the frequency of the light waves that the person on the planet sees. Okay, those two things are not necessarily the same if either the source or the observer are moving. Okay, so keep this in mind. What I want you to do now is I'm going to show you a couple examples of this, and then I want you to come back and read through this again and try to think about it a little bit more. All right, so what I want to do is start by talking about just a stationary source and a stationary observer. And there's nothing crazy about this, but here's how this is going to work. All right. So let me begin the screen here. Boom. All right. And so what we've got here is in the middle of the screen. All right. So in the middle here, what we've got is our source. And over here, we've got our observer. All right, and so what's going to happen here is when I hit play, the source is going to create waves of some sorts. Maybe they're sound waves. All right, so check it out. Here we go. Boom, boom. So he's creating waves. Boom, 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 boom. And the observer gets it. Boom, 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 at that same frequency. All right, so if both the source and the observer are stationary, then what happens is the frequency that the observer experiences is the same as the frequency of the source. There's nothing weird about that. All right. If you and I are standing in a room and I throw 2 tennis balls at you a second, then you're going to get hit by 2 tennis balls a second, right? It'll be fast, but there's nothing weird about this. Okay. Where things start to get weird is if either the observer or the source begins moving. Okay, so that's going to be the next deal. All right, so now watch what happens if our observer starts moving. All right, I'm going to skip this back to the beginning, and I'm going to make a sound every time the observer gets hit by a wave. All right, so let's scoot this back to the beginning, and we're going to hit play. All right, so our observer is making waves, or our source is making waves. Now the observer is going to get hit. Boom, 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 boom. So when he started moving, he gets hit more often, and now, boom, boom, boom. He gets hit way less often, right? So I want you guys to see that again. So the source is creating waves. Boom, 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 boom. And the guy gets hit. Boom, 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 boom. Until he starts moving. Boom, 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 boom. Quickly. And then when he's moving away from the source, he gets hit less often. Boom. 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 All right? So here's what we just learned. All right, so what we saw there is that if the observer was moving towards the source, if they're getting closer together, then the frequency that the observer experiences, is greater than, it's bigger than the frequency that the source was creating, right? Remember, when the observer started moving towards him, I was saying boom, faster, right? Okay, and then after he passed him and started moving away, then the frequency dropped. So now the frequency that the observer experienced was lower than what the source was creating. Okay, go back and watch that again if you don't get that, all right? So now the next question is this. What if the source moves, but the observer doesn't move? Okay, that's where things start to get a little bit more interesting, all right? So let me show you what happens there. All right, so we are going to get rid of this. Skip to the next video. All right, so our source is going to create the same waves, but now he's moving. And look what the waves do. Since he's moving to the right, the waves are closer together, right? Let me pause this here for a second. So look what's happening. All right, so in front of him, right here, the waves are very close together, right? The distance between the waves is small, so you've got a small wavelength, but that doesn't change the velocity of the waves. And so what happens is the observer gets hit with a big frequency, right? Whereas over here in the back, now your wavelength is way bigger, and so the observer is going to get hit with a smaller frequency. But either way, the velocity of the waves does not change. Okay, so I'm going to skip this back, and I'm going to say boom again. Once for the observer that is getting closer to the source. So there's two observers here. There's the blue one and the green one. All right, so let's skip this back and watch it again. So the observer in back is getting hit rarely. Boom, boom, boom. That's for the green one. Boom, boom, boom. Small frequency. Whereas the observer in front is getting hit at a high frequency. Dang it. The observer in front is getting hit with a high frequency. You got to wait for that first wave to get there. But once that first wave gets there, watch how quickly he gets hit. Boom, 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 boom. All right? So, oh, don't watch this one yet. All right. So, once again, the result that we get here is the exact same. For the observer on the right side of the screen, the source was getting closer to him, and that observer got hit with a higher frequency. It's the same thing. And for the observer on the left side of the screen, the source was moving farther away, and so we had this same result. All right? So that's what the Doppler effect does. When the source and the observer are getting closer together, the observer hears a bigger frequency, and if they're getting farther apart, there's a smaller frequency. Okay? So now the question is, what happens as that as the source moves faster? Okay, so right here what we've got is a drawing where the source is moving, but he's going a lot slower than the wave he's producing. So he's moving, but not very quickly. All right, and so what you can see is the waves over here are a little bit closer than the waves over here, right? You've got a small wavelength and a slightly bigger wavelength, right? But what's going to happen is as our source goes faster and faster and faster, the difference between this wavelength and this wavelength gets bigger. In other words, these guys are going to get closer together, these guys are going to get farther apart. Okay? So here we've got a source that's moving, but it's moving much slower than the wave that it's producing. Okay? And that's important. It's, at this point, the object is moving slower than the waves it's producing. All right? So watch what happens. If the source goes a little bit faster, then you get this. Notice, now there's a bigger difference between how close they are here and how close they are here, right? And if it goes even faster still, then you get this. All right? So the idea is, as the source goes faster and faster, the waves in front sort of bunch up, so your wavelength gets smaller and smaller, which means the ones in back get bigger and bigger. So if you're an observer in front, you're going to get hit with a big frequency, right? Because these waves are so close together. If you're an observer in back, where the source is moving away from you, then you're going to have a much smaller frequency, right? Okay. So the screen, I think, summarizes what the Doppler effect is all about, and I think we're going to stop there because I don't think I can do the next chunk in less than 20 minutes. All right, so it says, notice anytime the observer and source are moving towards each other, the observer is going to experience a frequency which is higher than the frequency the source is creating. All right, and if they're moving farther apart, then the observer experiences a lower frequency. All right, so I'm going to stop there.